Hi, my name is Philipp Kuehn and I'm presenting you our research paper OVANA, an approach to analyze and improve the information quality of vulnerability databases. This is a work by the Science and Technology for Peace and Security Chair at the Technical University of Darmstadt. Vulnerability databases are an important information sources in the field of IT security, and major players in this field are the Common Vulnerabilities and Exposures and the National Vulnerability Database, both covering over 155,000 entries. A vulnerability entry is a composition of the following information: an ID, which is an artificially introduced identifier, references, which are previously known information about this vulnerability, in this case a mailing list, a description, which is a human-written description about this vulnerability, the Common Vulnerability Scoring System information, short CVSS, which basically states the severity of the vulnerability. In this case, it's a critical vulnerability. The Common Weakness Enumeration, short CVE, which in this case is the incorrect permission assignment for critical resources, and the Common Platform Enumeration, short CPE, which basically is a structured format for the platform information of this vulnerability. In this case, it's an application by the vendor Akeon, and the software is called Rufus. And this vulnerability has already an information quality problem, because the structured information for the weaknesses cover only the CVE ID 732. However, the description also states additional weaknesses, here marked in red, which could be related to this vulnerability but aren't. And this brings us to our research questions. What are quantifiable criteria for the assessment of information quality in vulnerability databases? And which distinct information improves the information quality of the NVD? We conducted a preliminary analysis with the goal to identify whether the structured information of vulnerabilities alone are sufficient enough for their identification. First, we extracted structured information, in this case the CPE, CVE, CVSS version 3. The CVE identifier was not used in this case because it's an artificial identifier and does not describe the vulnerability at all. Then we implemented a simple clustering algorithm to cluster vulnerabilities, and then we tried to extract additional information, in this case vulnerable path and additional CVE information like we have seen in the example, using regular expressions. The results of the preliminary analysis showed that we were definitely able to improve the average cluster size by decreasing it, and we identified future problems. First of all, weakness information are sometimes missing, like we have seen in the example. Second, the outdated CVSS version 2 standard is used. Third, freeform descriptions are not fully utilized, like we have seen in the example. Then we identified missing CPE information. For example, the description might state specific versions of software which are affected by this vulnerability, which are not captured by the CVE. And last but not least, libraries are counted as the product they are used in. This might be problematic if the library is used in different products and the products only watch for vulnerabilities related to this library, and then they might miss some vulnerabilities. In our research, we focus on problems 1, 2, and 3, and problems 4 and 5 are left for future work. With this, I present you the concept of our implementation of the tool OVANA. First, our dataset is composed of 146,000 vulnerability entries from 1999 until 2020. 3,000 of these entries between 2015 and 2020, which includes CVSS version 3 information, are labeled by 2 IT security experts. The labels include the software name and software version. Despite not using them in our research, we capture them for future work. This is followed by CVSS related labels, attack vector, attack complexity, privileges required, all the parameters that are used in the base vector of the CVSS version 3. The weakness information capture the CVE information, and the vulnerable function and vulnerable path are our take to improve the National Vulnerability Database's information quality. These labels are based on the previous problems we identified. And the label descriptions are then used as basis for training and testing of our deep learning modules. The architecture looks as follows. We have the original NVD data. Then we have an information quality module which quantifies the information quality of the original database and the updated database. We have a named entity recognition module which identifies named entities in the descriptions. We have a CVSS value prediction module which predicts the CVSS values for each parameter based on the named entities. And we have the updated National Vulnerability Database with the updated information. The named entity recognition module is composed of different submodules which are individually tagging each token with the according tag. So for example, the software name tagger goes over each token in the description and tags each word which might be related to software name with the according tag. The CVSS module is also composed of different submodules. These submodules are based on the CVSS's parameters, attack vector, attack complexity, privileges required, and so on. And with this we get our first pipeline. The named entity recognition module pipes all words with the tags to the related CVSS submodule. For example, the words tagged with AV or attack vector are piped to the AV or attack vector CVSS value prediction submodule. This is done for all CVSS parameters. If the NVD's description does not provide any information about CVSS parameters, the named entity recognition cannot identify any named entities, and hence the CVSS submodule would use then the NVD's original data. And if the NVD's original data does not provide this information neither, we use the worst case assumption defined by the NVD. So for example, for the attack vector submodule, we would use the worst case network attack to provide at least some information for the CVSS score. This way, our CVSS module aligns the CVSS vector with the NVD's description. The information quality module analyzes the National Vulnerability Database's information quality based on content-based information quality criteria. Why? Because processing criteria, like for example the delay until the information reached the NVD or the download speed by the user using the NVD, are impossible to catch without outside data sources. And since we want to analyze the NVD's data based on the NVD's data alone, we do not use outside data sources. We settled on the following metrics. First, the accuracy, which is basically comparing the predicted and original CVSS scores. And then the completeness, which identifies missing fields in the entry. And the uniqueness, which is basically the clustering algorithm, and it additionally penalizes the large clusters. More details about these metrics can be found in our research paper. The overall information quality is then the sum of all metrics, and one note on the side: the lower the values of the metrics and the overall information quality, the better the information quality. This brings us to our evaluation. The named entity recognition module scores high values for frequent tags, like for example the software name, software version, and user interaction. And it scores lower values for infrequent tags. Here we applied an oversampling technique to increase the representation of infrequent tags in our dataset. An excerpt of our precision, recall, and F1 scores for our deep learning modules can be found below. The full table can be found in our research paper. Similar, like the Named Entity Recognition module, our CVSS module also scores high values for frequent tags. In this case, this is the confidentiality impact or user interaction, and scores low values for infrequent tags. In this case, the privileges required or integrity impact. We try to improve the scores using the oversampling technique of the Named Entity Recognition module. However, this was not successful in case of the CVSS module. An excerpt of our scores can be found below, and the full table is available in the paper. For the information quality, we improved the overall score by over 51%, which translates to a significantly better information quality. This is also reflected by the graphs on the right. The completeness was reduced by over 30%, and events like the CVSS version 3 introduction are also reflected in the data. On the lower right, we see that the reduction of completeness after 2015 is reduced to a minimum, whereas beforehand it stayed around 40%. For the accuracy, we used the following assumption: that the predicted information is more aligned with the original vulnerability information than the current CVSS information, and this is the reason why we added the accuracy only to the original information quality. The uniqueness is the main driver of the information quality score, and with this we found several peaks of the data. The first peak in 1999 results from a lack of structured information. The peaks in 2012 and 2017 are based on batch-added entries, in which over 70 entries are sharing the complete same information. Despite the fact that we were able to reduce the uniqueness score, this is problematic for our Named Entity Recognition module, because even the description was the same, and hence we were not able to identify distinguishable information, which could be used to resolve these clusters. This brings us to our contributions. We have 5 of them. 2 theoretical contributions, which are a definition of an objective information quality metric and the proposition of a novel partially explainable machine learning pipeline with the 2-step approach we used, and practical contributions which extract additional information from freeform descriptions, in our case the vulnerable function and vulnerable path, and we might be able to guide security experts and practitioners during a CVSS assessment due to the increased transparency of the CVSS scoring through the interim results of the machine learning pipeline. However, we do have some limitations which could translate into future work. For example, the information quality, we use only 3 metrics: the accuracy, completeness and uniqueness, and we do not compare our results with other research in this area. And on the machine learning side, we saw that training data was limited, which resulted in a partially bad performance. This could be resolved by increasing the training data by crowdsourced labeling processes, or using sophisticated data augmentation techniques to exponentially increase the data set. This concludes this presentation. In a preliminary analysis, we showed large clusters of vulnerabilities using structured information alone, the CPE, CVE, and CVSS. We identified further information quality problems within the NVD's dataset, some related to the CPE, others related to this unused information in the description. We tackled the definition of an objective information quality metric for vulnerability databases and implemented a tool, OVANA, which improves the information quality of the NVD by over 51% solely using the NVD's data alone. Thanks for your attention, and I'm ready for your questions.